Hello, my name is Ioannis Farmakis, and I'm going to be presenting on the qualitative assessment of multidimensional UAV photogrammetry models for computer vision applications in landslide investigation. Having in mind the landslide conceptual model and the theory, we as human beings and specifically as engineering geologists can interpret our observations, our visual observations using our cognitive system in order to generate landslide inventories with further categorizations like the one depicted on the right from the Washington state in the US. However, today with reality capture technologies such as UAV photogrammetry, but not only that, we have the potential to very precisely reconstruct the terrain in 3D and to leverage computer vision in order to automate such a task. Computer vision is an interdisciplinary scientific field that deals with how computers can be made to gain high-level understanding from digital representations. In this regard, geographic object-based image analysis has been very popular in the field of landslide identification from digital images, especially since the democratization of satellite imagery in the early 2000s. The GeoBia workflow, a typical workflow, consists in two main steps. The first one is the segmentation, which is the process of building image objects that are groups of pixels, and then the classification process that merges and classifies these newly formed entities into meaningful classes based on the semantics that come from domain expert knowledge. The pixels and the image objects, they have very significant differences when compared as information carriers. For example, the pixels have constant size and shape and also implicit location versus the unique area and outline information derivatives and statistical descriptors of the interior of an image object. Image segmentation is a critical step in GeoBia. The move from the traditional pixel-based model to an object-based contextual model has also changed the objective of segmentation from pixel labeling to object partitioning. Today, with UAVs, we have increased resolution of the available GeoBia input data for a site-specific landslide application, and the goal is to move the GeoBia applications with the UAV-based GeoBia applications from regional scale that are based on satellite imagery to the site-specific scale and with the greater resolution. Photogrammetry provides a multidimensional geographic data, and for this reason, the aim of this work is to examine what dimensionality space is more effective to perform the segmentation at for site-specific GeoBia landslide applications. We have considered in the study two case studies, namely Prusos and Red Beach respectively. They have different geometric characteristics, different landslide mechanisms, and different geomaterials involved. All the details regarding the geologic setting and all the geological characteristics of the sites can be found in the corresponding section in the full paper, as well as in the references that we provide there. And from photogrammetry, we generate different kinds of models. Orthomosaic, which is the 2D RGB raster representation. I can also generate 2.5D representations known as digital surface models or DSMs, which include elevation information to each pixel. We can also fuse orthomosaic and DSM and maintain two kinds of information in the 2D representation. And we also have 3D point clouds that represent the terrain in fully 3D directly with points sampled in space. And to make that an equivalent to the 2D image, make a 3D image, we use voxel grids, which is each voxel is the 3D equivalent to a pixel, is essentially a cube that divides the space uniformly, and as the name of the voxel defines, a volumetric pixel. and the edge length of each voxel of this cube defines the resolution of the image the same way that the edge length of a pixel defines the resolution of a regular 2D image. In the methodology we follow, we use this after fusion and voxelization. We use this 2D, 2.5D, and 3D models, and they go through the segmentation pipeline in order to compare the results. The segmentation is a two-step process, a very common pipeline in computer vision that starts with a generation of super pixels or super voxels in the 3D that are groups of pixels and small groups of pixels. And then we use a graph clustering in order to further cluster these ones based on their dissimilarity and in the color and the spatial domain. The UAV survey used the multi-rotor platform DJI Phantom 4 Pro and a specifically designed survey plan for landslides that is depicted on the figure here on the left. The characteristics and the properties of the survey can be found on the table on the right, and also the quality result of the structural motion process that was used to process the raw image and generate the final products. The first component of the segmentation pipeline is the simple linear iterative clustering, known as SLIK. This is one of the most popular methods for the tessellation of an image into superpixels or supervoxels if it's a 3D. We have extended that in the 3D by developing the same algorithm to operate directly on a voxel grid using open source Python modules. It essentially includes an iterative local implementation of the k-means clustering algorithm simultaneously at multiple areas of the image, as shown on the picture on the right. A superpixel, or similarly a supervoxel, is an image patch that is better aligned with object boundaries that are rectangular or a cubic patch in the 3D. SLIK defines smaller search areas, minimizing the complexity and execution time as compared to searching the whole image. And the SLIK has two advantages. The first one is that the number of distance calculations in the optimization is dramatically reduced by limiting the search space to a region proportional to the superpixel size. This reduces the complexity to be linear in the number of pixels, and this is where it takes the linear iterative clustering name from. And also it's independent to the number of superpixels. The second advantage is that it used a weighted distance measure based on the equation on the bottom left that combines color and spatial proximity in the feature space, while simultaneously providing control over the size and the compactness of the superpixels. The objective of superpixels or supervoxels is to group pixels and voxels into perceptually meaningful regions to replace the rigid structure of the 2D or 3D grid. Subsequently, these generated uniform entities are further merged using GraphCAD clustering. To implement GraphCAD clustering, the superpixel and supervoxel assembly must be modeled as a weighted undirected graph. The nodes represent the superpixels or supervoxels, and the edges connect adjacent nodes. Each edge is weighted by the feature space dissimilarity of the nodes that it connects. A GraphCAD is the removal of edges which make the graph disconnected with a minimum cost. However, sometimes optimizing with a minimum cut cost does not provide the best results. And here on the figure on the right, we can see a case where minimum cut gives a cut partition. And for this reason, the normalized cuts have been proposed that take into consideration the whole feature space of the image, of the graph. And you can see the equation with a normalization here at the bottom, and more details in the mathematical expressions are provided in the article that I refer on the bottom. In the full experiments, we used different configuration of the segmentation algorithms in order to assess their switchability with regard to the dimensionality. And specifically, you use different superpixel and supervoxel resolutions We also used and different orders of magnitude in the normalized cut cost threshold. And all of the experiments and the results and the visualization can be found in the full paper. However, I have selected some segmentations here that are very characteristics of the result. And we have here segmentation applied to 2.5D model and also to the 3D model with the same configurations. And we see that steep areas as the scarp here are better delineated by the algorithm operating on a 43D grid. And here on the right, we can see another perspective in the 3D view. The same for the areas that I have highlighted here in the yellow ellipses. That we see that the flank of this landslide is better captured, and the elevation is taken into account in more precisely. And again, one more example here, the green that it turns out that again we can delineate with the same configuration better some critical features in when operating in fully 3D space. In summary, the goal of a segmentation method in landslide scenes is to provide segments that define the boundaries of elements such as the extent of the landslide at first, and secondarily the scarp, the depletion zone, the accumulation zone, the elements at risk, etc. Reality capture and 3D reconstruction methods such as structure from motion allow the acquisition of detailed geometric and spectral information of even inaccessible areas. The pre-processing of the generated models and the way one manipulates these geodata is an essential part in the transition from the digital model to a more intelligent model. To achieve useful segmentation of a landslide scene, the digital model must provide sufficient information relative to the investigated scale of analysis. In steep settings where many landslides occur, critical elements of the landslide morphology, such as the scarp, the flanks, and may not be adequately modeled using raster operations on top-down view projections of the terrain. Operating on fully 3D terrain representations seems to not only include more information in the spatial domain, but also unlock hidden aspects of the model. However, the generated 3D point clouds remain largely unexploited in GeoB applications yet. If you are interested in following our research, this is the contact information that you can use. And at this point, I would also like to thank all my co-authors, my supervisors, Dr. Jean Hudson and Dr. Nicholas Lahopoulos, for their efforts for this work. Thank you all for your attendance, and I'm happy to take any questions.